one of the first things I want to do before we get into the presentation proper is I want to demonstrate something that I'm going to quickly introduce it right now, and then towards the end of the session we're going to circle back around and make more sense of it, but there are some reasons that I'll clarify later that I want to kick this off right now. And if we could switch to the demo machine briefly, that would help me out. All right. So as I said, I'm going to demonstrate something really quickly that's only going to make a little bit of sense right now, and we're going to make it make more sense before we're done. But I've got a couple of microservices running out on GCP right now, and notice the URL there begins with mn-backend. So I'm sending a request to this backend service, and I'm sending a request to /hello/Jeff is all that's really important about that URL, /hello/Jeff. And we get back a response that is what you see there, hello space Jeff. That doesn't look terribly interesting, but there are a number of interesting things going on that we'll get to. So when I send a request to the backend service at /hello/Jeff, we get a response like you see there. And if I send a similar request to another service called the front-end service, what we're going to see is a similar response, but the response is all uppercase. And what we've got in place is there are two microservices deployed to GCP right now. One is the backend service, one is the front-end service. The backend service knows how to create this greeting, hello Jeff. The front-end service is calling the back-end service and converting the message to uppercase, just so we've got something happening in the front-end service. That's really all I want to get into around that, what those services are capable of right now. But what I want to do while I'm pressing into the rest of the talk is I want to deploy a new version of this back-end service, and that's going to allow me to talk about some interesting capabilities that I think you'll find interesting. So I've just made a code change to our backend controller. There where it says, a moment ago it said hello plus name, that's the service. This is the service we're invoking from the command line. I'm going to make a code change, and instead of saying hello Jeff, it'll say Google Next says hello Jeff. And I want to deploy that service to GCP. App engine deploy, just like that. And I'll let that get far enough along that I know that I don't have a typo there. That looks good. Okay, so while that's running, if we can go back to the slides now, I appreciate the help. We're going to come back to that and talk about a number of interesting things going on there. All right, so my name is Jeff Brown. I am a partner at Object Computing, and I'm one of the co-founders of a couple of open source frameworks that we develop and support. One of them is the Gradle framework, which is a JVM web framework that's been around for over a decade and has been tremendously successful, and we're very proud of that. And I'm also the co-founder of another technology called Micronaut, which I'm going to spend more time talking about today. I help run the Gradle and Micronaut practice at Object Computing, and you see some contact information there. I'm easy enough to track down if you want to get a hold of me. And speaking of getting a hold of me, we do have a booth set up out here in the exhibit hall. The booth number is on the very last slide, so that'll be easy enough for you to find later. I believe it's 1163. Please stop by the booth if you have, and talk to us if you have any questions at all about what I'm going to introduce today or anything at all that we can help you with. All right, so Object Computing is headquartered in St. Louis, Missouri, which is where I happen to live. We are a distributed team. We've got folks all over the country and elsewhere. We've got a number of folks in Europe and Australia. But our headquarters is in St. Louis, and as I said, that's where I happen to live. Object Computing has been in business for about 25 years and has been an open source company since the very beginning, which is really interesting in part because in the mid-90s there were not very many open source companies, and Object Computing was one of them. We heard some great talk this morning during the keynote about Google's commitment to open source. And I'll get back to that point a little bit later in the presentation, but we've done some really interesting things with Google that relates to our open source software, and I'll get to that. So Object Computing is the home to both the Gradle and Micronaut team. It's really one big team. We don't have two separate teams managing these two technologies. It's one team of engineers, and as I said, I'm the practice lead there at Object Computing, helping manage all of those efforts. We've got deep expertise in a number of areas, some of them that you see listed there, industrial IoT, machine learning, blockchain consulting, and cloud engineering. We're going to find that most of you are probably aware that Google is a great fit, GCP in particular is a great fit for building these kinds of applications. and Micronaut is a really great fit for building these kinds of applications and deploying them to GCP. And I'm going to spend some time this morning pressing into some details that will support all of that and help that make more sense. This is a partial list of clients at Object Computing. Some of these names we saw earlier during the keynote. Some of these companies are large Google users. One of the interesting things about this partial client list is notice that it spans really a lot of industries. We've got the semiconductors, telecommunications, finance, aerospace. So Object Computing has served many industries over the last 25 years, and it turns out that's a great fit for what I want to talk about today, because Micronaut and GCP, these are not technologies for aerospace, and they're not technologies for telecommunications. They're general purpose technologies that can be used everywhere. And that's just one more reason that our technology and GCP is such a great fit together. And by the way, I cannot see past the first few rows in a room this big, so raising your hand will not help. I probably won't see your hand. I'll try to make some time for Q&A at the end, and there are mics here where we'll take those questions if we do have time. But as I said at the beginning, if you've got any questions at all that we don't get to today, please come by the booth and see us. I intended to mention that earlier. I apologize for that. All right. So I mentioned just really quickly, I want to talk a little bit about the Grails framework, and then I want to get into Micronaut and GCP. But talking just for a couple of minutes about Grails is going to help us make sense of some of the stuff that I want to press into. So Grails is an open source framework for building web applications for the JVM, and it's been around for over a decade. In February of 2008, is when we shipped Grails 1.0, and the framework predates 1.0 by a year or so. So the framework's been around for 11 or 12 years, we'll say, and it's been tremendously successful over that time. So we're very proud of the Grails framework and the business that we have built around that. One of the things that has enabled Grails to be as relevant and as important as it's been for as long as it has been, for over a decade, is the fact that the technology has evolved considerably since the beginning to stay relevant to the way that folks want to build applications today. So in 2007, when we started all of this, REST was, certainly the idea of REST existed, but it was nowhere near as big of a deal as it is today. Every enterprise builds REST services today. And so in the very beginning, there wasn't a whole lot of support for REST in the Grails framework. You could certainly build REST services with Grails, but there wasn't a whole lot of support for building those kinds of apps. And over the years, as REST got more and more important, Grails stayed ahead of that by adapting to the way that people want to build applications. So over the years, we built more and more support for publishing REST services. And today, we have really terrific support in Grails for building REST services. And that's an example of the technology evolving over the years to stay relevant. And that's an important part of the technology's longevity. GORM falls in that same category. GORM is the ORM tool that's part of Grails, and it's always been part of Grails. It's been part of Grails since the very beginning. And in the very beginning, GORM was really just a layer. It was conceived to be a layer on top of Hibernate. We added a bunch of really cool and powerful capabilities on top of Hibernate and made it easier to take advantage of what Hibernate had to offer. But that's what GORM was in the very beginning. And then over the years, GORM has evolved to adapt to the way that people want to use a technology like GORM. So for example, early on we introduced JPA support. So you could pull out Hibernate and plug in whatever JPA implementation you like. And then fast forward a few years past that, and the so-called NoSQL databases started gaining a lot of traction and momentum. Databases like MongoDB and Cassandra, and there were a whole bunch of those. People wanted to use GORM to talk to those kinds of databases. So we evolved GORM further. And today we've got GORM implementations for Hibernate and JPA and MongoDB and Neo4j, which is a really interesting graph database, Cassandra. We've got a bunch of GORM implementations. The point there is that the technology has evolved to stay relevant and to keep itself an important part of the landscape in which these technologies play. So as we're confronted with changes in the landscape, the technology changes to deal with those. And now, today, and in recent years, one of the changes that we've had to confront and come up with solutions for a whole category of challenges is microservices, right? When we first started building Grails a decade ago, monoliths were the way that most folks built and deployed JVM web applications, right? You put your whole application in one big WAR file, drop that WAR file in Tomcat or whatever server container you prefer, and that's how you deploy web applications. And if any part of that application needs to be updated, you have to update the whole thing. And there are benefits to a monolithic architecture like that. There are drawbacks to a monolithic architecture like that. But that's how applications, by and large, were built. And those are the kinds of applications that Grails was initially designed for and prioritized for. Now, as more and more enterprises want to build microservice architectures, there's a whole suite of challenges that come along with building those kinds of systems. And that's another example of changes in the landscape that our technology needs to adapt to. So we recognize those changes, those new challenges. Google recognizes those challenges. And you recognize those challenges, or you will as you start looking into migrating to microservice architectures. There are lots of good reasons to deploy applications in that kind of architecture, but it's not all the benefits don't come for free, right? There are new challenges that you'll have to confront with microservices that maybe you didn't have to confront with monoliths. And what we're doing with Micronaut and our integrations with GCP is we're trying to make it as easy as possible for folks to build those kinds of systems and take advantage of these really robust services that Google has to offer with minimal burden on the application development team and minimal complexity in the application code base. We recognize that this a whole new set of challenges that relate to microservices. And we had to decide what to do about that. So when we wanted to evolve GORM, we realized, hey, we've got this great tool for dealing with relational databases. People want to use that, they want to use that tool to talk to non-relational databases. And we figured out how to evolve the technology to deal with that. With microservices, that was one of our options, right? Well, one of the things we could have done was continue to evolve our current technology to be more and more compatible with the way that are more and more compatible with microservice architectures. That's one approach we could have taken. We decided not to take that approach. Rather than evolve our current technology to be a better fit for microservices, what we decided to do was design a whole new thing from the ground up, specifically designed for microservices and specifically prioritizing microservice architectures, and that's what Micronaut is. Micronaut is an open source framework for building microservice applications for the JVM. It's been designed and optimized specifically for microservices. So certainly you can build monoliths with Micronaut, and people will do that, and people will have success with that. But we're designing and optimizing the framework specifically for microservice architectures. The runtime is very lightweight. It's based on Netty, which offers a bunch of really positive characteristics. It's really fast, it's really lightweight, it's got a bunch of really great reactive support in the framework that we're taking advantage of at the Micronaut level. So the runtime in Micronaut is based on Netty, and as I said, it's really, really fast and really, really lightweight. We'll come back to that point a little bit later. Micronaut is a polyglot framework, so the languages that we've got proper support for in Micronaut include Java, Kotlin, and Groovy. And all of our annotation processing so all of the annotations that we support in Micronaut work across all three of those languages. The exact same annotations, they all yield the same net effects. So if you would prefer to build your systems with Kotlin and you prefer to take advantage of all the benefits that Kotlin has to offer, you can do that and take advantage of everything that Micronaut has to offer. If you prefer dynamic languages like Groovy, we've got terrific support for doing that. If you're a Java shop and don't want to introduce any of these other non-Java JVM languages, you can build your whole systems with Java. And the languages can mix and match within a project. So within a single Micronaut service, you can have Java code and Kotlin code and Groovy code, and it all just plays well together really, really well. So it's a polyglot framework for the JVM. Micronaut is really not just one thing. It's really a whole portfolio of things. And that portfolio of things includes some components like an aspect-oriented programming engine and a dependency injection container and an HTTP client. And a number of these components can be used separate from the rest of Micronaut. So for example, our dependency injection container that we've built in Micronaut has some really interesting, innovative characteristics to it that I'll talk about. But that DI container is usable separate from the rest of Micronaut. So if you're building a Java application and you want a DI container, you can use Micronaut's DI container in that Java application without using any of our HTTP server stuff or without using any of the other components that are part of Micronaut, which is great. Some of the interesting characteristics of our dependency injection container all have to do with the fact that our DI container doesn't do any runtime reflection, which it turns out is a really big deal. One of the reasons that our current technology before we built Micronaut, so Grails in particular, one of the reasons that Grails is not a terrific fit for building microservices has to do with Grails' dependence on the Spring framework. And the Spring framework is terrific. There's all kinds of really, really great stuff that Spring does, and those are the reasons that we built Grails on top of the Spring framework. But Spring is expensive in some ways for certain kinds of applications, and a lot of that has to do with Spring's dependence on runtime reflection and dynamic proxies. So what we've done with Micronaut is we've eliminated all the runtime reflection and all the runtime proxies and replaced that with a really sophisticated ahead-of-time compilation compile time tricks to do all the stuff that we otherwise would have done with reflection at runtime. So all of our annotation processing is all configured at compile time. Our whole dependency injection container is all configured at compile time. No runtime proxies, no runtime reflection. And that is where a lot of our performance benefits are coming from in Micronaut, and where a lot of other positive aspects like much smaller memory footprints. So we'll talk a little bit more about that as we press on. As I said, Micronaut is being designed and optimized specifically for building microservices. And in a microservice architecture, you don't have one thing, you have numerous things, and maybe lots of things, right? You have this whole architecture of components communicating with each other. So a request comes into the system and hits component A, and component A calls component B, and component B calls component C, and that's how these microservice architectures work. In each one of those interactions, you've got a client and a server, right? When A calls B, A is a client and B is a server, and when B calls C, B becomes a client and C is the server for that particular communication. Because that's the way microservice architectures work, Micronaut prioritizes both sides of those communications. So we've got a really, really sophisticated HTTP client, as well as a bunch of really cool and powerful server-side stuff, and we'll look at examples of both of those. Some of the priorities that the framework has include things like developer productivity. Time to market is really important and really valuable, and we recognize that. So we make a lot of design decisions specifically targeted at contributing to developer productivity. Another attribute that goes along with that is code simplicity. In a Micronaut application, you're going to write considerably less code than you might with other frameworks. And all that is related to not only time to market, but ease of maintaining and extending the system over time. So we prioritize developer productivity and code simplicity while embracing a familiar programming model. So folks who are used to building applications with modern JVM web frameworks will see a lot of the same kinds of idioms show up in a Micronaut application. So for example, you can write a service class and annotate that service class with @transactional, and a bunch of really cool and powerful transaction management related stuff will be associated with that class. What I just now described isn't new and isn't innovative. Those capabilities have been around for a long time, but how we're doing that is new and innovative. And again, that has to do with all of our compile time annotation processing stuff, which allows us to rig up things like the DI container all at compile time and not rely on any runtime reflection or runtime proxies. And a particularly important part of all of this that we want to focus on today is our ease of integration with these really, really sophisticated enterprise scale type cloud services. So if you're going to build a microservice architecture and deploy it to GCP, you're probably going to want to take advantage of things like Cloud SQL. and Kubernetes and all of these robust services that Google has provided. One of the things that Micronaut is doing is making it very, very easy to take advantage of those services without having to take on much of the burden or the cost associated with the development burdens associated with building systems that take advantage of those services. And the framework is really, really fast. Runtime performance is another one of the things that's an important attribute of that affects all of our design decisions. So we want you to be able to build the thing quickly. We want it to be simple, easy to maintain, and easy to extend code. We want you to be able to integrate with these a robust suite of cloud services that are out there. And we need the thing to be really, really fast at runtime. And in fact, it is. So some of the important benefits that Micronaut has to offer include runtime performance that shows up in terms of startup time for your services, as well as performance while the application is running. So a typical Micronaut service can be started up in something like a second. Sometimes less than a second, sometimes a little bit more. It depends on what the application is doing. But a second puts you in the neighborhood. It's not like 20 seconds or 30 seconds or even 10 seconds. 1 second startup time puts you in the ballpark. Minimal memory requirements. So a small Micronaut service can run in about 10 megabytes of heap, and depending on what your application's doing, will dictate how much above that you need. But that kind of represents the overhead or the tax associated with the framework itself, which is really, really quite small. We're not going to look at a whole lot of code here today, but we'll see a little bit of code. But one of the attributes of systems built with Micronaut is the code really is quite simple. As I said before, we're embracing familiar programming models and embracing or enabling easy integration with cloud services. So a small Micronaut jar file might be about 8 megabytes that's the size of the jar file. And of course, the more code you put in your project, the jar file is going to get bigger. But that, again, represents kind of the overhead that the framework brings along, which is really quite small. And you see the startup time and heap requirement numbers there. And I want to take just a minute to talk a little bit about these. These are attributes that relate to microservices in ways that they don't necessarily relate to monolithic applications. So think about memory consumption as an example. If you're building a monolithic application and that application requires a gig of RAM to run, in your development environment, you start the thing up by with Gradle or whatever tool you're using to start the app, and you allocate a gig of RAM to the thing, or maybe the startup scripts are doing that for you and you don't even really think about it. But allocating a gig of RAM to your monolithic app may not be that big of a deal because there's only one of them. In a microservice architecture, there's not going to be one of them. There's going to be maybe lots of them. So try to start, if you've got a monolithic servlet container-based web app, and try to start, say, 30 of those up concurrently on your development machine. And it's just not going to work for a number of reasons. And one of those reasons is you're going to run into memory issues. In a microservice architecture, you might really want to do that. You might want to start up a whole bunch of services on one machine in your development environment. So the memory requirements become, they factor into that equation differently than they would for a monolithic application. And in your deployment environment on the cloud, where you're paying for VMs that based on how many CPUs and how much RAM you're allocating to them, adding up all of those large memory requirement machines in your cloud environment can get expensive. So these are examples of attributes that manifest differently, or they affect your microservice architectures differently than they affect monolithic applications. So Micronaut embraces, one of the things that Micronaut does is it makes it very, very easy to take advantage of these robust cloud services that the cloud providers make available. So we've got really, really, really great support for service discovery by way of console. We've got support for Eureka. We've got support for Kubernetes. So we support all the major service discovery engines. And this, again, this is an example of a thing that's important in a microservice application that's not important, or maybe not even relevant at all in the context of a monolithic application. If in a monolith, there's only one, so there is no discovery, right? You're not going out and trying to find these other things to communicate with. So service discovery is an example of a capability that the framework provides to make it easy to take advantage of something like service discovery that is part of that new suite of challenges that microservice architectures bring along. Configuration sharing is kind of the same thing. If you got lots of microservices deployed out in your cloud environment, you probably want them to share configuration, and we've built really, really sophisticated systems to make it easy to take advantage of distributed configuration engines in all the major cloud providers. We've got some really interesting client-side load balancing stuff built into our HTTP client that if I've got some time, I'll be able to demonstrate a little bit later. We've got support for building message-driven applications. We've got integrations with technologies like Kafka. We've got really great support for serverless computing and a lot more, right? So the Micronaut is not just a framework for building REST services, right? It's not just that. It is that, but it's a whole bunch more than that. And a lot of that has to do with all of these cloud native capabilities that we've built right into the technology. This quote here that was posted on Twitter, I believe this was posted before we even got to release 1.0, which we released this past October. This person recognized something that, what he's recognizing is that one of the things that Micronaut is and does is it enables you to very easily build these systems that take advantage of all of these services like Kafka and Consul and Zipkin and MongoDB and JPA and on and on. That's one of the things that Micronaut is it's an enabler, it's an accelerator for folks who want to take advantage of these robust cloud services without having to spend lots of time and development effort building the integrations with those systems. So Google has been a priority for the Micronaut team at Object Computing, really pretty much the whole time that we've been working on this, but certainly right now Google is a priority. We've partnered with Google. Object Computing is an official Google partner, and we've got really great support in Micronaut for taking advantage of GCP, Google Cloud Services. So we've got support for Kubernetes and Stackdriver and gRPC, and there are others. Some of these, Google's actually contributed the support to the framework. So for example, this week we'll be releasing Micronaut 1.1. And in 1.1, we've got some new support for Stackdriver and gRPC. And some of that was developed by Google, and they contributed those efforts to the open source software, which is fantastic. And that's a little bit of putting your money where your mouth is with respect to what Google said this morning during the keynote. Google says that they're committed to open source, and Google really is committed to open source. And this is one small way that manifests. Right? So I want to take a look at a little bit of code, and that'll help us tease out some things that I think you'll find interesting. So this could be a Java class in a Micronaut service. And so we've got a controller. What makes this thing a controller is it's annotated with that controller. Those of you who might be familiar with the Grails framework might recognize that in Grails we have lots of conventions in place that do things like if you've got a class whose name ends in the word controller, it becomes a controller. And those conventions do not exist in the Micronaut framework. So what makes this a controller is not the class name. The class name could be anything. What makes it a controller is it's annotated with that controller. And there's a method in this controller that's annotated with that get. So if I send a get request to /hello/something, this controller action gets executed, and then I can do whatever I need to do. And there's a lot I could do in this controller. There's a bunch of interesting data marshaling going on in both directions for reading and writing the body of the request and the response. There's a bunch of reactive stuff. There's a whole lot you can do in a controller. This example is literally a hello world kind of example. But that's a controller that could be in a Micronaut service. And in fact, the service that I was interacting with from the command line at the very beginning of the session looked a whole lot like that. Right? So we've got this back-end application that has a controller in it. Then I might have another service. This is not in the same application. This is a whole different service that's part of our microservice architecture. This is the front end, right? So I've got a back-end piece that's maybe talking to a database and doing whatever it's doing, and separate from that, I've got another microservice that is in the front end. And this thing needs to call or wants to call the backend service. That's how microservice architectures work. You've got these components making calls to each other. This is one microservice making a call to another. And the call is happening at that last line of code there, where it says backend client.hello name. That's actually making an HTTP call to some other service. And there are a number of interesting things going on in that method call, and we're going to be able to press into just a little bit of that. Notice that backend client that we're interacting with there was injected into this controller by way of dependency injection. And so we've got a constructor here called, that accepts a backend client as a parameter. And at compile time, Micronaut will recognize that that constructor is there and create all the instructions that it takes to create, not only create this thing, but to pass the required dependencies as constructor parameters when it is created. So the backend client is being injected into this controller, and that's one of the things I want to look at. And this is the backend client. And this looks terribly benign, right? There's really nothing interesting that's apparent from looking at that source code. It's not even a class. It's just an interface that has a method in it, and there are a couple of annotations. As uninteresting as the source code looks, what's actually going on is quite interesting. So at compile time, what the framework is doing is creating an instance, creating a class that implements this interface, and in that class will be a method called hello, and when you call that method, an HTTP request will be made to some remote service, and we'll figure out how we know about where that remote service is before we're done. But we're making an HTTP call to some remote service and passing. So if I call hello and pass Jeff as a parameter, then the request will be sent to /hello/Jeff. Right? So we've made it very, very easy to make an HTTP call. But this is more than just that. So when I annotated this interface with @client, that's what makes this thing an HTTP client. And the value that I can specify there can be one of a number of things. So where you see backend URL inside of the curly braces, that's a variable. It's a config variable. So whatever the value of backend.url is, that'll be inserted at this point. So instead of using a config variable, I could put a URL there. I could put https:// and have a URL there. And now when I make calls to this method, that URL represents where the remote service is that I'll be communicating with. And there are other values that backend URL could have. But let's press on here. So now I've got some configuration in the back end and the front end represented here. Remember, these are two separate services, two separate applications, we'll say. In my development environment, I want to be able to run these things concurrently. I want to be able to run the back end and run the front end. And because of that, they need to run on different ports. So in my backend config file, I've configured the thing to run on port 8082. In the front end config file, I haven't specified what port I want it to run on. So by default, it'll run on port 8080. So now when I start these things up, the backend is on 8082, the front end is on 8080, and the value of backend.url is what you see in this config file, localhost 8082. So the config file on the right is in the front end project, and that's the front end project being told where the backend service is. The backend service is on localhost 8082. And that works fine in my development environment, but what about when I deploy this to GCP? My backend service is not going to be running on localhost 8082. It's going to be running someplace else. So these are the config files that I would have in my project that support my development environment. In addition to those application.yaml files, you can have config files with names like application-gcp.yaml. Now, that -gcp means something special to Micronaut. So these config files will only be loaded if the application is running on GCP. So if I run these applications in my development environment, these configs are in place. When I build those applications and deploy them to GCP, these configs are in place in addition to the application.yaml configs, and these settings take precedence. So in the backend service, I've got application-gcp configured so the service runs on port 8080, which would be the default value had I not changed that in the config file there on the left. Remember, I set that to 8082 for the benefit of my development environment. When I deploy to GCP, I want that service to run on port 8080, so I've got a supporting config there. And likewise, in the front end, when I'm running on GCP, that's where the backend service is running, is that URL that you see there. So instead of looking at localhost 8082, we're looking at the URL that you see there. That's where the front end will be making calls to to get data from the back end, right? And this is one small example of support in the framework specifically targeted at GCP. And here I'm just configuring a port number and a URL, but all of your application config, any of your application config that needs to be different in that environment, in the cloud environment, GCP cloud environment in particular, we provided a place for you to put those configs, right? So now I'm ready to publish these applications to GCP, and so I've got a couple of app.yaml files. The URL down there at the bottom gives you the full reference for all the things you can do in these app.yaml files. I've kept these really, really simple. So on the left is the backend service, on the right is the front-end service, and I think they're configured exactly the same except for the service names. So I've got some auto-scaling in place there. We can configure how much RAM is being allocated each of these environments. But I've got config files for both the services is what's relevant there. And now one of the last pieces is one of the ways to deploy Micronaut services to GCP is you can use Google's App Engine Gradle plugin, which is really, really simple to use, right? So I add it to the class path of the build script, as you see up in the upper left, apply the plugin, and then down at the bottom left, you see where I'm configuring some things that the App Engine plugin needs. So in particular, I have to specify where is the jar file that is the application that I want to deploy. When I run the deploy, I want to stop the previous version. I want to promote the new one to automatically become the kind of the main one. And project OCI Micronaut, that's just the name of the project where I'm deploying these things. So if we were to so if I were to execute the App Engine deploy Gradle task, the command you see on the right there, that's literally what I would type in to deploy this service to GCP. In fact, that is what I typed in at the beginning of the service, or the beginning of the presentation, to deploy a new version of our backend service to GCP. So I've added just a few lines of code to the build.gradle file, executed a Gradle command, and that service has been deployed to GCP, and we'll get back to that in a little bit. We'll see the new version of the service responding to requests. But again, what I wanted to point out here is how easy it is to deploy Micronaut services to GCP. Just a few lines in your build.gradle file. A similar, sort of roughly a similar amount of code would be involved in doing the same thing with Maven. Micronaut has great support for both Gradle and Maven. Really, you can use any build tool that you like. But we've made it very, very easy to deploy applications to GCP. And one more example of GCP specific config is in addition to application.yaml, you can express your Micronaut config in executable Groovy code. And now you can have arbitrary logic in your config file for generating config values. And in this particular case, reaching out to Google's metadata server to grab some secrets about my database URL, my database username, my database password. So this is code that I can commit to source code control. There's no passwords, there's no secrets here. This code only gets evaluated when the application's running on GCP. And when the application's running on GCP, I'm getting all my database credentials from the metadata server there. So you've got a lot of flexibility there. Micronaut is great at really as a component of many parts of your application architecture. So the easy one to think about is microservices, right? So people build microservices, they deploy them to GCP, and Micronaut is terrific for that. But Micronaut is also a great fit for certain kinds of edge devices. So I've got a bunch of Raspberry Pis here that in just a minute, I'll spend a couple minutes talking about what's going on there. But we've got Micronaut services running on these Raspberry Pis doing some interesting things. I have Micronaut code running on an Android phone. So I've got a Google Pixel 3, and I've got some microservices deployed to GCP. I've got a Micronaut application running on my phone, a native app running on the phone built with Micronaut that's making calls to those GCP services. These particular edge devices are not making calls to GCP, but they very well could. So we've got really, really great integration support in Micronaut for participating in a number of areas of your architecture. So it could be the case that you've got Micronaut apps running on your edge devices. You've got Micronaut services running on in your cloud environment. You can have Micronaut apps running on mobile devices. And we've got there are attributes of the framework that make it really, really compelling in all of those environments. And I'm going to press on here and try to get straight to some demos. So if we could switch back to the demo machine, that would be helpful. There we go. So that's a picture, for those of you who are far away and can't really see, that's a picture of this thing, right? So what I've got is I've got 4 Raspberry Pi Zeros and 2 Raspberry Pi 3s, and we're going to see a diagram that will tell us a little bit about what's going on in that environment. Can we switch to my demo machine, please? There it is. All right. Very good. So what I want to do is, I apologize. Could we go back to the slide for 1 minute? There's a slide there that I want to look at, and I appreciate the patience of the AV folks there. There we go. Sorry about that. So this diagram represents what's going on the Raspberry Pis. So we've got an SPA front end that we'll see in just a minute. It's very, very simple. It's making requests to some Micronaut service called the home controller that's running on one of these Raspberry Pis. And we've got 4 other Raspberry Pis that are all running copies of the same service, and those services are all communicating with a database. So SPA talking to kind of a gateway service. That gateway service is communicating to a number of services on the back end, and those back end services are communicating with the database. If we could go back to the demo machine again, I would appreciate that. All right. So this is I need to get connected to that network. All right, now if I refresh this page. So this is the SPA application, and the data that's being represented there is not terribly interesting. It's just a list of company names. You see OCI, Moog, and Tesla there. This is really the interesting part, the part that I want to focus on. And notice that green box, the 4 small Raspberry Pis are called MN Pi 1, MN Pi 2, MN Pi 3, and MN Pi 4. And in the UI, I can tell which of those devices handled a particular request. So as I reload this page over and over and over again, we're round-robining through all of those back-end services. So on that diagram where you saw 4 company services, we're round-robining through all of those services. And what I'm going to do right now is I just unplugged one of them. So I unplugged MN Pi 1. So now 2, 3, and 4 are still operational, but Pi 1 is down for maintenance, or it's crashed, or for whatever reason, it's not operational right now. And I'm able to do that without interrupting the rest of the system. So I'm still round-robining through the other devices. That request was handled by number 4. That request was handled by number 2, then 3, and then 4. So we just took this guy out of the mix, and the rest of the system continues to behave as we would hope. And I want to look at a little bit of the code that's involved in making that happen. So if I were to... and I'm going to do this really pretty quickly. This is the HTTP client that's being used in the front end to communicate with the back end. And notice on line 12 there, where the @client annotation is the word companies. What's happened is all 4 of the company's services have started up and registered themselves with Console, our service discovery engine that's running on one of the devices. So on the front end, when I want to communicate with those devices, I've annotated this interface with @client companies, and what will happen when this client is initialized is Micronaut will reach out to the service discovery engine and find where are all the company's services. So it discovers these 4 Raspberry Pis dynamically, and it's round-robining through them, doing client-side load balancing to round-robin through all those devices. And then when one of them disappears, the round-robining just skips over 1, 2, 4, 1, 2, 4, 1, 2, 4, right, if number 3 is out of the mix. And I don't have to write any of that code in the application to take advantage of that. So here in my home controller, this is where the call, this is in the front end, that's the call to the back end. There's no code here related to round robining. There's no code here related to retry logic. I'm just saying go get the companies from the back end service. And all of the complexity and stuff that it takes to make that happen is all handled inside of this HTTP client. So the client-side load balancing is built into this client. The retry logic is built into the client, and now my application code is kept very, very simple, and it's very, very easy to take advantage of or get to send communications to whatever is happening in that back-end service. Right? I hope all that makes sense. And I need to get back on the public network now. Google Next 2019. There we go. All right, so you see the commands there that I executed at the beginning of the session. And now if I go back to the back end again, now we see Google Next says, hello, Jeff, right? That's evidence that we're communicating with the version of the service that I deployed at the beginning of this talk. And then if I go to send a request to the front end, we'll see that the front end is communicating with that updated instance of the back end, right? So at the beginning of the session, I made a trivial code change and deployed a new version of the service to GCP. And what it took to deploy that service to GCP is basically the Gradle config that you saw in the slides earlier. Take just a super quick look at that. All right, so here's my backend project. In my build.gradle file, I've got the App Engine plugin added to the class path. I'm applying the plugin here, and down here somewhere right here is the code that tells the plugin what to do when I ask it to deploy a backend, deploy this service to GCP. There's really, you've seen all the complexity involved in deploying the Micronaut services to GCP. This is all of it. There's no pieces that I'm doing any hand waving over. So it's very, very simple to build and deploy Micronaut services to GCP is the bottom line.